Okay, hi everyone. Welcome to this GTP seminar. We're very happy today to have Eric Finster, who is going to tell us about the Infinity One category of types. Please, Eric.
Okay. Well, first of all, thank you very much for the invitation. It's a pleasure. I've heard a lot about your center, so it's cool to be, even if virtually, so to come talk to you guys. So yeah, so today I'm going to talk about the Infinity One category of types. Maybe this wasn't such a great title because I think the majority of the talk is going to be about a kind of approach to thinking about coherent higher structures inside of type theory. And so most of the talk will probably be concerned with a description of this approach and sort of my ideas about how we can address this. And then we'll see that the Infinity One category of types is a kind of application. So what's the main problem? So again, I apologize because I've been a little bit sick recently, so I hope I won't cough too much during the talk, but I'll do my best. Yeah, so the major sort of outstanding problem with the type theoretic view on higher algebra and higher mathematics is that type theory so far doesn't let us describe infinitely coherent algebraic structures, or no one has figured out a way to let type theory in its current incarnation describe higher algebraic structures other than types themselves. And so just as a little bit of background, I don't know how familiar everyone is with this sort of type theoretic approach, but I can explain maybe in a couple of words how I came to it, and maybe that will give some background to people who aren't familiar, who might be coming from classical homotopy theory or topology.
Laptop doesn't like that.
Sorry?
I think it's a function of this, probably his.
Yeah, probably.
I think it's the connection of that thing to the internet, because these two work fine. So it just means there's a connection to that thing.
Okay, I can't quite hear the discussion that's going on, but if there's a question, don't hesitate to.
No, sorry, Eric, there was a glitch, I think.
Okay.
Connection.
Oh, I see.
It's fine, yeah.
Okay. No problem. So yeah, so my background was in classical homotopy theory, and so I was acquainted with a lot of the ideas really going back to the 70s, I think, or maybe even earlier, of kind of realizing that all of algebra sort of repeats itself in a homotopy theoretic context. So anything you want to do with groups and rings and modules and so on, you can almost always find interesting homotopy theoretic analogs of this. And people like Waldhausen put forward the idea of brave new algebra, thinking about commutative ring spectra as the higher analog of commutative rings, and so on. And this kind of leaves open this question: well, why does mathematics seem to repeat itself in the context of homotopy theory? And so when I learned about this approach, the connection between homotopy theory and constructive mathematics in around maybe 10 years ago now, maybe a little bit more, it kind of provides an explanation for this, because it says that, well, if you look closely at the foundation of mathematics and you're careful about equality, in the sense that you keep track of equalities as data, then that version of mathematics that comes out just is this version of homotopy theoretic mathematics, where higher algebra is just algebra. And the difference is that in this type theoretic approach, we have a logical system which treats equality as data from the get-go for the very fundamental objects. And so this kind of, suggests that you should be able to build a really nice foundation for higher mathematics, what a logician or proof theorist or type theorist now would think of as proof relevant mathematics, mathematics where proofs are fundamental objects, should be, so type theory should be a nice foundation which lets you arrive at these higher dimensional algebraic structures without passing through the sort of not niceties of set theory, where you have to argue about different models and the properties of these models, and where notions of equivalence don't correspond with the notion of equivalence you intended, and a lot of these sort of model dependent annoyances that you have to sort of deal with in a set theoretic foundation would sort of be pushed away, and you would always be working with invariant higher algebraic objects. So that's, for me, coming from homotopy theory, has always been the promise of type theory. And the 10 years on, the fact is that this simply has not come to pass because of this problem that type theory does an exceptional job of doing this for groupoids themselves, so for types, but not for structured types like infinity one categories, E infinity rings, A infinity rings, all these, objects that we sort of want to be talking about. So the way I want to frame the discussion today, and sort of my approach to fixing it, is to think about the notion of sort of presentation, because presentations, I claim, in higher algebra, and I don't think this is I'm saying anything revolutionary here. I'm just I think lots of people know this. I behave very differently than they do in set theoretic mathematics, and so I want to sort of frame it in that context. And so one way I would sort of argue is that type theory gives you this basic theory of types, which behave like homotopy types, which behave like higher algebraic objects. But it doesn't, in its current state, provide you with any fundamental description of how to present those types, how to describe presentations of types. And this is the sort of problematic thing that has plagued, I would say plagued. I mean, there's lots of great things you can do with type theory already as it is, so it's not a plague, but it definitely is a cap on the things that we've been able to do with it somehow. So just a couple words about this. I mean, in set theoretic mathematics, when we think of the presentation of an algebraic structure like a group or a ring or a field, this is some kind of extra data. The generators and the relations that these things satisfy, we turn them into data, but they're not really sort of part of the group itself. I mean, the presentation is sort of separate for it from the structure. But when we move to higher mathematics or proof relevant mathematics, then all of our algebraic objects should sort of remember all of the relations that they have and the relations between the relations and so on. That's what sort of thinking about higher mathematics is about turning proofs into data that needs to be kept track of. And well, in that case, the sort of distinction between the algebraic structure you're thinking about and the presentation of that algebraic structure kind of dissolves a little bit, because the relations are actually, in this context, part of the structure itself. And it turns out many higher dimensional structures have a description or a definition, which is essentially they are presentations of the structure you want with a certain closure property. So if you're familiar with classical homotopy theory, you can think about this just, the canonical example would be simplicial sets, where general simplicial sets are presentations of homotopy types, and the actual homotopy types, the sort of vibrant ones or the well-behaved ones, the ones that we consider algebraic, have a certain property, which is just this Kahn lifting property. So I think this is a real theme for many different types of higher algebraic objects, that they can often be described as a collection of data which is sort of saturated in some sense. So they're just presentations where there's enough presenting objects around for them to behave like algebraic structures. So I think that the distinction between the object itself and the presentation of the object, I mean, there's still a distinction to be made, but it becomes a little bit more blurry. So sort of in light of this, sort of perspective on how we need to treat higher dimensional algebraic objects, it sort of seems reasonable that if you're setting out to have a foundational theory of these objects, that presentations are also a kind of primitive, that you need to provide yourself not only with the basic theory of types, but also with the theory of presentations of types, that these two things are sort of inextricably linked in a way that they aren't necessarily in set theory, where we can just define presentations as other collections of sets in a simple way. And so this idea that type theory should be equipped with presentations, I wanted to point out that it's not particularly new. In fact, there's a certain sense in which the type theories we deal with today, if you open a proof assistant like Agda and Koch and so on, they go beyond our mathematical presentation of what type theory is, because they have things like inductive definitions and so on, and they even have special support for inductive definitions and so on. And there have even been certain people who have presented type theory. There's a very nice description of type theory due to Connor McBride, where he says very explicitly that he's going to create a type theory where there's a universe of types and there's a universe of inductive definitions, the data of inductive definitions. And what the type theory does is it gives you a primitive which takes a presentation and turns it into a type. So even this idea of equipping type theory with a sort of parallel universe of presentations of types is not new. It's existed in the literature. The difference is that he's considering classical inductive definitions, which I'll have more to say about that in a bit, not higher dimensional things. So now that we have homotopy type theory, we sort of realize that presentations are even much more complicated than we thought they were, because the data of a inductive presentation is relatively easy to write down, but the answer to the question, what is the data of a higher inductive presentation, is essentially the problem that's under discussion here. So how to define a simplicial type, or how to define a cubical type, or an opotopic type, or so on. Okay, so now when I talk about presentations, there's some flexibility here. So just like I said, in classical homotopy theory, one of the most common ways to think of present a homotopy type is with, say, a simplicial set, or even a topological space, if you like. Cubical sets will do many. There are many by now known models that you can get to model homotopy types. In fact, there's whole classes of them. These Savinsky versions and test categories and so on. So it's well known that there's many ways of presenting. And so what I'm going to use here for my notion of presentation are presentations of higher dimensional types, and later we'll see higher dimensional structures using opotopes. And I'll try to explain some of the reasons why I think this is a natural choice for type theory as we go. So with this kind of background filler underway, so what do I mean concretely about adding a notion of presentation to type theory? Well, so what I'm going to do is I'm going to directly axiomatize. I'm going to add opotopic types, which are going to be these infinite collections of data presenting a type. I'm going to add them as a primitive. I'm going to add them primitively to the theory. But when I say that, they're going to be added primitively in a way that computes, so that has a definition. So if I ask you, if I ask the type checker or the computer or the formal language, what is an opotopic type of, say, dimension 3 for any fixed dimension, it will compute and tell me you need to produce this amount of data to have such a thing of dimension 3. And so on. So the thing that I'm going to do differently, which avoids this sort of coherence problem of us not being able to define these things in ordinary type theory, as far as we can tell, is that the definitions, the equations that make these types well defined, which I would have to prove if I was trying to define these things in type theory as it is, I'm going to take these as belonging to the meta theory. In other words, I'm going to make them compute. I'm going to give these equations normal forms in a way that lets the definition go through. Okay, so concretely, what is an opotopic type? Well, it's just going to be an infinite sequence of type families, where you can think of it as each type family indexed by dimension is going to assign a collection of, say, here. Do you see my cursor, by the way, when I move it like this? I'm not sure if that's a...
Yes.
Okay, in dimension 2 here, where I'm highlighting, it's going to be assigning a collection of 2-dimensional cells to every valid 2-dimensional boundary configuration. Okay, so just like you can imagine, a simplicial type would assign a set of n simplices to every well-formed n-1 boundary or whatever. So for historical reasons, I would call these boundaries frames. This is a terminology introduced by Byers and Dolan in their paper on these subjects. And so this already lets us give a description, a definition in the sense that I was saying before, which will compute, saying that an opotopic type of dimension n+1 is just a pair of an opotopic type of dimension n plus a family assigning to every valid boundary configuration made out of the previous data a type of fillers. And I'll give some pictures of this kind of thing in just a second. Okay. So fundamentally, you can think of it as a collection of n cells of various shapes for all n. And I'll describe why this how this is problematic to define in ordinary type theory and how you get around that. Okay, so just real quick, one of the nice things about opotopes is they have an explicit sort of pictorial language which works in all dimensions. And so here I'm sort of drawing a couple of these for you. So to say that something is of dimension 0, I'm just going to put it in a box and call it X. So this will mean X is sort of an object. In dimension 1, the only valid boundary configuration is this one, where I have the 2 blue boxes, which are 2 objects, and where I have the arrow F, which I think of as mapping between these 2 objects. So in dimension 1, the collection of valid boundaries is just a pair of 2 objects, and the collection of fillers for that pair you should think of as arrows connecting them. In dimension 2, the boundary, so here you can see there's no boundary piece. In dimension 1, there's a single boundary piece. In dimension 2, there's going to be 2 boundary pieces. The 0-dimensional piece, which consists of 3 objects, X, Y, and Z. And then the 1-dimensional piece consists of an arrow F from X to Y, an arrow G from Y to Z, and an arrow H from X to Z. And then an element of the family X2 would be an alpha filling this configuration. Now there turn out to be infinitely many valid configurations in dimension 2, so it's more, this is a richer sort of geometric structure than just simplices. And then in dimension 3, you get things that look even more complicated. But all of these diagrams, you can see they're very tree-like, and you should really think of opitopes as kind of the analogs of higher dimensional trees or higher dimensional term algebras or things like this, which is why I think they dovetail very nicely with type theory. Okay, so the basic shapes end up being a little bit more complicated, but this is just to give you a basic intuition for how these things look like. The opitopic type itself is the data of all the purple information, right? The 0-dimensional fillers, and then the 1-dimensional fillers, and the 2-dimensional fillers, and so on. So to keep along with our definition, actually, well, I'll show you this in a second. So again, if I have an opitopic type of dimension n, it determines a type of its valid boundary configurations. And I'm going to show you really quickly how it does that. So every opitopic type also, it's going to come equipped with an endofunctor of types over this type of boundaries. Which you can think of as the monad which associates to any collection of fillers the type of well-formed pasting diagrams built from these fillers. Okay, so there's a sort of monad. You choose a filler, and I apply PD, which is for pasting diagram, and this is going to output the collection of well-formed pasting diagrams built on this collection of fillers. And opitopes are really related to monads because they're essentially determined by the fact that these PD things are in fact monads. Okay. So as an example, so if you're in dimension 0, then you start out with an opitopic type, and the relation is just this. You start out with your x1, which is just a relation between the type X. It'll be X cross X to itself. So you can think of this as a collection of fillers or a collection of arrows. And if I apply PD to that thing, it's going to give me the collection of strings built from those relations. So the collection of sequences R, S, T. So you can think of the first monad here as the monad of lists. Given some collection of data, it's going to return lists of those data. And so the higher monads are analogs of sort of tree-like configurations of data. But all of these monads, each monad in dimension n depends on the definition of the monad in dimension n-1, and so on. So these monads get more and more complicated as you raise the dimension. But once you have this notion of knowing that this monad exists, then this tells you how to create. Remember, I said that an opitopic type was going to be a previous dimension opitopic type and some collection of fillers on the frames. Well, in order to finish this definition, I need to tell you how to define the frames. And the answer is that once you have this PD monad around, the frames are just pairs of an element of the type of the filling family you gave and a pasting diagram built from it. So for example, if I'm in dimension 1, I start out with this 0-dimensional piece. I have one relation, and then I have a pasting diagram of elements of this relation. And this determines a frame where I take the pasting diagram and pair it off with the U element, which I think of as the target. And this is now a new frame, a new valid boundary in the next dimension, which can be filled by a new piece of data. Does that make sense? So the frames now, once I have this, it's a pair. If I have an open-topic type together with a relation, then the frames in the next dimension are a frame, an element of that relation, and an element of the pasting diagram on that relation. So again, this is a definition. It's not super important that you understand exactly the geometry. It takes a while to get used to it. But here I'm just showing you that the frames also compute after one dimension into something defined in the previous dimension. Okay, so now we've sort of defined open-topic types, and as soon as we know what frames are, we know what frames are as soon as we know what pasting diagrams are, right? So this is how the definition is unwinding. Now, so the central issue where things break, the reason we can't do this in plain homotopy type theory, the reason how we haven't been yet, is that you have to define the monad structure on this thing I just said is a monad, the pasting diagrams. You need to show that it's a monad, and the well-formedness of the pasting diagram monad in dimension n+1 depends on the fact that the previous dimension was actually a monad in a coherent sense. Okay. So if you try to do this in type theory, what you find is that to define the monad in dimension 2, you need to know the monad in dimension 1 is associative. And to define the monad in dimension 3, you need to know that the monad in dimension 1 is 2 associative, and so on. And this leads to an infinite regress, because you need to prove that the thing at the bottom is infinitely coherent in order to finish the definition. But the definition is supposed to be the thing which is telling us what it means to be infinitely coherent. So this is where we get into this stuck thing. On the other hand, so what I'm going to do to sort of break this is I'm going to take these operators that make PD into a monad, and they are now primitives of the language, and they have normal forms which make them associative and unital. Okay, so that's the basic idea here. We lift this theory of presentations exactly by making these monads compute nicely. We make them have nice normal forms. So I was going to show you how this actually works in practice, but I had to recompile Agda to make that work. And it looks like it succeeded. So let's see if it's going to let me. Actually, I'm going to open it up and show you. This may not work because I had to reinstall my computer, and then I had to reinstall. So let's see. Okay, well, unfortunately, Agda is not working here for me. Okay, well, so it's going to be black and white. It's not going to be nicely. But here, I just wanted to show you basically how this works is that, in fact, you do give a definition of open-topic type, and then you define the monadic structure exactly as I've just said. And then here's where we go outside the realm of Agda, which is that we postulate these rewrite rules. We say that that this monad is unital and associative, and you can see them right here. So we tell Agda that these rewrite rules are primitives of the theory, and then the definitions they work as I said. So if you go through this, you'll see that. Let's see, open-topic type of dimension n is, well, here I've defined it inductively instead of recursively. It's an open-topic type of dimension n, and then a family on, well, I've called them indexes here instead of frames, so some of the naming is different. But just to show you that you can work this out, and then at some point you need to actually define the monad laws, and they turn out to be remarkably simple. There's a unit law. There's a sort of, you need this intermediate grafting of trees, and then this notion of substitution of trees, and they're actually totally sort of trivial to define from a functional programming point of view. Those are those, going back to my slides, these are these monadic operations. They have an easy definition. This definition doesn't type check in all dimensions unless you assume that they're already associative and unital. So we break the impasse by telling Agda that they're associative and unital. Okay. So that's the idea. And when you do this, you get a version of open-topic type which computes, it unfolds, and so on. So that's the sort of good news. And then there's the bad news. So what does this actually buy you? And the answer is, on its face, it doesn't buy you that much at all. so having defined like the notion of opotopic type, as I just did, sort of by force, I add the equations. You don't make any progress, very much progress at all, because you find immediately that you need to know what a map of opotopic types is. And this also needs some additional equations in order to type check. And so that's kind of not totally reassuring, because of course the danger of doing what I've just done, adding some equations, is that I don't want to be in a situation where every time I need to prove something new, I need to modify the theory by adding new equations. So certainly that would be sort of problematic, because I would be saying that, well, I can prove any theorem I want because I just add the equations that make that theorem true. So so that's not going to be a legitimate strategy in the long term. So but what I sort of propose here is there is a very natural place to say what the rest of the equations I need are going to be. And the basic thing is that once I've defined these opotopic types, these infinite families of fillers, which we had trouble defining, but I fixed by making it a definition, a primitive, that gives us the type of presentations. These opotopic types are the types that present underlying homotopy types, but what we need is the type theory of presentations. And so this comes from the fact that, like type theory has an interpretation in sort of any pre-sheaf category. So as soon as I have like a basic, I've chosen what the sets are, then I can interpret type theory in diagrams of sets. And so what I sort of contend is that not only do you need the notion of presentation, you also need the rest of the type theory associated to these presentations. So these will let you make constructions on presentations in parallel to the constructions you make on type. It lets you create new presentations out of old ones and so on. So you want, in the analog I was saying before, where as I said, some people have added, universes of presentations to type theory before. Well, you want those universes to be closed under certain operations. That's basically what I'm saying. The presentations of types should have as much structure as the types themselves. There's various ways to set this up. The most natural thing is to sort of think about the classical way we understand type theory. And the sort of algebraic structure it presents is what's often known as a category with families, or a contextual category or something like this. It has a category of context, and it has a pre-sheaf of types and a pre-sheaf of terms. And so you can axiomatize all that in this setting as well. You say that the opotopic types are going to serve as contexts. You axiomatize the notion of map, and that will serve as the substitutions. You axiomatize the notion of, well, there's various choices. Dependent opotopic type. Another way to do that is to axiomatize the universe, which is what I'm going to do instead here. So let me describe really quickly, once you have opotopic types around, what the universe of opotopic type looks like. Okay, so what do I mean when I say that? Well, so if you think of the project here as axiomatizing both a base topos of spaces as well as some particular topos of diagrams over that spaces, then that topos of diagrams is going to have an object classifier, and that's the object I'm interested in describing. So it's the opotopic type. It lives in the pre-sheaf category of opotopic types. And so what does it look like from the perspective of type theory? Well, it's an opotopic type where x0, the type of points, is just a type. And where x1, so a morphism between two objects, which, as I've said, are types, is a relation between these two types. And more generally, the cells of higher dimension, they look like what I would say is opotopically shaped relations. So for example, if I looked at a cell of this shape, this simplex shape in the universe, it would be exactly a type family S, which took an element of A, this type down here, an element of B, this type down here, an element of C down here, an element of F relating A to B, an element of G relating B to C, an element of H relating H, and then return to type family. So S would itself be a type family over its boundary. So somehow the way to think of this is that all that the cells of the opotopic type of opotopic types are types, although you have to take that to mean types in the context of their boundary. But in any case, this is sort of what it would look like. So a simplex in the universe, the universal opotopic type is just types on each 0 simplex, relations on each 1 simplex, and then higher dimensional relations of the appropriate shape on higher cells. Okay, so that's what the universe looks like. And then this universe has a universal family, because if I have an opotopically shaped relation, then an element of that shape living over it is just a choice of an element of that relation. So I would choose an element of A, an element of B, an element of C, an element F living over F, an element G living over G, relating the 2 elements that I chose before, and then an element S in this relation that I showed down here, which is relating all of those elements themselves. Okay, so once you have this, you've defined opotopic type, you've defined the universe of opotopic types as well as its universal fibration. So you can give all of these definitions again using some basic equations which make these things well defined. They need equations to compute, but you can add all of these things by hand. So once you have this, you've sort of going back to what I was saying, you've sort of internalized the type theory of opotopic types, because once you have substitutions, now you can talk about dependent opotopic types as maps from an opotopic type to this universe. And you can talk about, and many operations end up being definable. So pulling back opotopic types and things become definable, and so on. So you've sort of built a second level type theory inside of type theory by giving some equations. So let me pause here to sort of compare what I've done here with what is, I think, the main competing approach to the problem that I'm talking about today, to getting talking about coherent higher structures inside of type theory. So the main alternative approach, the one that was suggested actually by Voevodsky himself and then taken up by some other authors later on, is also to have 2 type theories in parallel. But the difference is that you start with the type theory of ordinary homotopy types, the type theory hot that you like, the good types, and then outside of it you add a second notion of type for which equality is sort of strict, for which, and in particular in this external theory, the second kind of type are the non-fibrant types, and they have essentially a set truncated equality. So the way you solve this coherence problem is you essentially kind of bring back the notion that sets are primitive. And now in this external theory, you can prove a lot of relations the way we do in classical mathematics, which is that if everything's a set, I don't need to worry about higher dimensional relations. And you can use this the second layer of set truncated non-fibrant types to solve coherence problems in the inner theory, the fibrant types that you want to talk about. So this is the main, I think, alternative proposal for how to have coherent structures in type theory. And so I have a couple sort of problems, not with the people who've developed this approach, but with the sort of with the picture that it proposes. So a first complaint is that sort of you add a notion of non-fibrant type, you add these, sometimes they're called exotypes or these sort of extra types which have special properties, but there's no explanation of what these types are. They're just abstract. It's just a second level type theory, and therefore you have all of the things that you would have in your ordinary type theory, like the natural numbers and pi and sigma, they're all repeated. So you get second versions of sort of everything. You get a set version of it and then a homotopy theoretic version of it and so on. And this is a little bit unsatisfying because why should you have two natural numbers? And then you get into axioms like, are these two natural numbers the same or not? And this seems like a weird thing to be arguing about to me. So the second complaint, obviously, is that, coming from classical homotopy theory, this is the way things are now, which is that we use sets to present homotopy types and higher structures. And so bringing that back in the realm of type theory seems a little bit like giving up the game, because the whole sort of promise of type theory was to eliminate having to, or at least for me, to eliminate the necessity to argue about set truncated presentations and the fact that these don't always have good properties. And so bringing it back seems like a step somehow backwards. And then the last one is that, I think the sort of central principle that makes this approach, this type theoretic approach go, is the univalence principle. This kind of like, I mean, more than anything, this is a sort of foundational principle, an idea about how mathematics should be, saying that everything we say is invariant under equality, under the appropriate notion of equality. And so if you add this second level of types and then truncate it, well, you've broken that principle, because it can't possibly apply to these non-fibrant types for the same reason it can't apply in set theoretic mathematics. So you also sort of give up one of the sort of core principles, I think, of the homotopy theoretic approach to mathematics. So what's happening here, what I've sort of described here, is also a two-level kind of type theory. Well, I'm sort of like accepting the fact that you need types as well as presentations of types. But here, the difference is that I've defined these presentations, these opotopic types, and you can think of them as the non-fibrant types, but they're defined in terms of the fibrant ones. So anytime something computes, anytime I look at sort of the next dimension, then the definition unfolds, and the dimension n+1 is defined in terms of dimension n, and so on. So here we've added a second type theory, and we needed the equations to do that. We need to modify the foundation to add those equations, but the result is that we have a second type theory of non-fibrant types, which are defined in terms of the fibrant ones. And this to me seems like a more natural presentation, because you don't add anything new, you just add the equations which make non-fibrant types well formed. And it also has the immediate consequence that that univalence applies to opotopic types in the same way it applies to types, because it will unfold, and anything you can prove about equivalence of ordinary types, you'll be able to prove about equivalence of opotopic types. So it sort of it preserves the sort of invariance principle that I think is necessary. Okay, so
Eric,
what can
I ask you a question on this point?
Yeah.
So I maybe missed how this works. It seems you're defining this ordinary one categorical monad on the underlying type system, right?
So
let me ask this way. What if you change a frame, say, by a propositional equality, by an equivalence? Does that, how does the
it will compute. I mean, so because frames are defined, so I think the definition I gave it sort of right here, they're defined in terms of a sigma type. So if I have an equality of frames, this will just split into, to give an equality of frames by univalence will be the same, or by how type formers work, will be the same as to give an equality of the previous frame, an equality of the things in the relation over that frame, and an equality of the associated pasting diagrams. And the pasting diagrams are defined as an inductive type, which you can compute the equality type of in the same way we usually compute the equality type of an inductive type. So everything computes, and therefore equalities of opotopic types are determined as infinite sequences of equalities of families, and that's why univalence applies. Yeah.
Okay.
So yeah. So it's true. Well, I mean, I can come back to this point. It's true that I said this monad, I gave its it's not exactly true to say that it's just a one monad. I mean, it is a coherent monad on arbitrary types. What we can't do is express the fact that it's coherent on arbitrary types. So instead of giving myself the task of expressing it, I've removed the fact that I have to prove those equations. But that doesn't mean they're sort of not there, right? I mean, that doesn't mean that it's not coherent. Just like, yeah. composition of functions, for example, in type theory is strictly associative. It's definitionally associative, but that doesn't mean that it's not well behaved on homotopy types. Does that make sense? Okay. I'll keep going. I mean, you can ask me more questions. Maybe I can clarify that more later on. Okay, so what can you do once you've done this? Okay, so well, first of all, once you have open-topic types around, you get lots of definitions. So you can define what you mean by an infinity groupoid. You can define what you mean by an infinity one category. What is a infinity planar operat? What is an infinity n category? You can do infinity category. You can do lots of stuff. You can beef up the notion of open-topic type to take into account symmetries, and then you'll be able to define symmetric versions of all of these. So the thing that I've worked on, like implementing, is the simplest version. There are more refined versions which can get you even more higher dimensional structures that you can define directly in terms of the presentations. Now, I sort of started off saying, and I think this is true, that that the sort of real motivation here is to have presentations of types. But once you have presentations of types, which are sort of like vibrant open-topic types, and I can talk about what that means, then you can vary that vibrancy condition and have lots of other higher dimensional structures. So I sort of think of the fact that this gives you a bunch of other higher dimensional structures as you having a theory of presentations, which you can now modify, which you can now decide what kinds of properties you want to impose on that presentation. So once you have this theory, also it turns out that lots of other things are suddenly now definable in this theory. So as I said, I've added a bunch of equations, right? I'm sort of unashamedly saying that we need to add some equations in order to sort of solve this problem. I've added a bunch, but as I said, the danger is, do I always need to add a new equation every time I want to make a new construction? That would be bad. But it turns out that once you've set up somehow the type theory of presentations, a bunch of new things become definable without new equations. For example, sigma and pi of these presentations can be defined using sigma and pi in the outer theory. If you have a type X, it should determine an open-topic type generated from its identity types, and it turns out that is definable in the theory. Things like the join of two open-topic types turn out to be definable in the theory. Once you have higher inductive types, then the realization, the reflection of an open-topic type back to a type is also definable as a higher inductive type. So this is just to say that you start, or at least it seems, I don't know how far this goes, it seems that you start to get a little bit of momentum because for all of these constructions, you don't need to add new equations. And that's the sort of theme, I think, of what I've been of this talk somehow, is that by sort of setting the bar a little bit higher and adding this type theory of presentations, we start to get some things that you can do. Once you have the join, for example, you can actually give a formal definition of infinity limits and colimits. Now, I don't know how far this continues. I'll say more about that in a second. And then there are some theorems that we've been able to prove with this. So, for example, you can prove that every infinity groupoid, in the sense I've just in the sense of the definition that arises from these open-topic types, is in fact determined by its type of zero simplices. And so this forgetful map gives you actually an equivalence between the type of types and the type of infinity groupoids. So this is a sort of, a basic check. Types are fibrant open-topic types. That's or infinity groupoids, which amounts to the same thing. So I just want to say it's not at all obvious that from the sort of structure that I've proposed, adding this to type theory, you would get out some theorems like this, but at least this much appears to be definable. It can be done. And then the sort of, I'll finish with the point of the talk, is that we can also do the infinity one category of types, and here's how. So recall that I talked about how the object classifier, the open-topic type of open-topic types looks. Its cells are open-topically shaped relations. And so let me say that a relation is fibrant. So this is a property of some particular cell in that universe. If given elements of all the relations decorating sort of the horn, the open-topic horn associated to it, the type of fillers, So the type, in the case we were considering this S, it would be given the ABC, F, and G, the collection of pairs H and S is contractible. That is, there's a unique output and filling cell. So this is actually an internal proposition on the universe in this second level type theory that I've sort of defined. And it defines a sub-object of this object classifier. It's the sub-object of fibrant opotopic relations. And the claim is that's going to be my definition of the infinity one category of types, that it is exactly this sub-object of fibrant relations. And the theorem is that you can prove that this sub-object is an infinity one category in the sense of the definition of infinity one category that arises from having opotopic types around. So this is it's not a totally trivial thing. I mean, you need to do something. The idea is completely obvious, but I sort of regard this as another example of something you can do with the kinds of equations that I've sort of proposed adding is you get this definition of the infinity one category of types, and you can prove indeed that it is an infinity one category. So I think this is basically the story I wanted to tell you. I finished a little bit early, but maybe that's okay. We can have some questions and so on. And so I think I'll stop here.
Great, thank you. Any further questions? All right.
Eric, sorry, you mentioned that you needed, I don't know where I talk. Hi. You mentioned
Hi.
that you needed okay. You mentioned that you needed more equations than just the ones governing the monad, but I don't know if you ever actually explicitly said what they are.
Yeah. Yeah. So for example, when you go to define substitutions, they're going to be maps of families. So I mean, you can just imagine what it is: a map of opotopic type. It's a map on the families, and then a map from the family in dimension 2 to the previous substitution applied to the lower dimensional pieces of data, right? So you're going to have an inductive definition like this, but where you're going to get stuck is you're going to need any substitution to commute strictly with the monad laws. So you'll need the sort of naturality of the monad laws under substitutions. That's a sort of example of the kind of equation that you'll need in order to make substitutions well defined. And roughly, I would say what basically happens is that this CWF that you've built now, this internal CWF has this extra structure of having these monad operations running around as primitives. And so roughly the equations you need is that everything in the CWF structure is compatible with these monad laws. That's sort of, and this becomes pretty systematic where, like I said, when you go to define substitution or morphism, you need to say that substitutions preserve the monad laws definitionally. That's the kind of equation that you're going to need. The same thing will happen for, as I say, it actually turns out that there's many different ways of setting this up, either in terms of substitutions or in terms of terms. So you can talk about opotopic terms of an opotopic dependent type, which might be slightly more type theoretical. And then you'll need to know that that terms are compatible with this monad law. So basically what ends up happening is you build this second type theory where everything is natural with respect to multiplication in the monad. Does that answer your question?
Yeah, thanks.
Yeah.
Okay. Any other questions for Eric?
Could I ask another one?
Of course. Go ahead.
Sorry, just to ask something just directly. Is this definition? Do you think this is still experimental, or do you think now that's it? That works? Is the claim that?
Yeah. Yeah. So the definition. So there's two ways that I can answer this. So this definition can be implemented in AGDA using some extensions where you allow yourself to add definitional equations. And in that sense, the theorem, for example, that I've claimed here is 99% proven in Agda itself, in the sense that you really literally can write the proof of this in a proof assistant extended with some extra equations. There's some difficulties with that, in that there's some engineering difficulties, and that Agda wasn't designed to do this, and I have to force it to do this by adding these equations, and this breaks some things, and so it works pretty well, but there's some unpleasantries that sort of keep you from blah blah blah, which I've progressively been working on fixing and so on. So what should happen is that a type theory like this should be implemented from scratch, because I've extended the meta language, in which case you would have much more engineering flexibility to make this kind of thing work well. So I should say, so in present day Agda, I have to like hack things in, and so it works 98%, and there's 2% of annoyances where things don't compute the way you wanted, and so on. That's an engineering issue. The probably deeper question that I think you want to know is like, is there any way of assuring that you get everything from this definition? And to that, the answer is that I just don't know. In the sense, and so I contrasted, I explained why this sort of two-level theory where you bring back set theory doesn't appeal to my philosophical convictions or whatever, and so I would like some kind of alternative to that. So the advantage that theory has is that it seems it seems very plausible that it's sort of complete, in the sense that anything that you could have proved in set theory using presentations, you'll be able to prove in this theory as well. So you don't expect it to sort of miss anything. You expect it to really be able to prove whatever you want, because you've brought back set theory. So that makes sense. Whereas what I'm doing here is kind of more like a minimal extension. I'm trying to find like the least amount of things that you can add that will preserve univalence and let you talk about higher dimensional structures. And so there's no guarantee, in a certain sense, that it's complete in the same way, because I may quickly come across, in my list of things I've been able to do, I could easily come across something that I can't do. And so I will say that there are some things that I still don't know how to do, but that's not 100% proof that they're impossible to do. And so the only way I know to go about this is to keep accumulating evidence and making constructions that show that more and more things are doable this way. That being said, I think there are, a couple of things. There are some theorems you could prove that would get you close to saying this is in some sense complete. Okay, a theorem along this lines might be something like the following, so you add opotopic types as primitives, but they're not defined as a pre-sheaf category of diagrams in the category of types. So what I've shown here today is how to define the infinity one category of types. That's great. So then what you might imagine is proving a theorem that says these opotopic types are equivalent to pre-sheafs in the category of types. And then once you've proven something like that, it feels like you're getting really far, because now anything you could do with the infinity one category of opotopic pre-sheaves, you can sort of now transfer back and forth across this equivalence to opotopic types. Do you see what I mean? So for example, if you are able to show that it's complete and co-complete and sort of satisfies some of these nice closure properties, then it feels like you're kind of showing that you've developed everything that you needed about opotopic types. I don't know if this answers your question, but so I would say the current status is that this works for some things, and I'm hoping that it will sort of lead to enough constructions and theorems that we can sort of be satisfied that we can carry out essentially, all of the theorems that we're interested in. Does that make sense? Is that a reasonable answer?
Thanks, yeah, that helps. But maybe you could help me with one point here. I'm not quite sure yet if I see how you specify the specific higher structures that we want to talk about. Suppose I next want to ask you to let us speak about E-infinity.
Yeah.
Okay. What do I have to do?
So there's two different ways. So one, as I said, there's many different actually flavors of opotopes. In fact, for every for every monad, for every infinity monad, well, Cartesian polynomial infinity monad or whatever, there will be an associated notion of opotopic type. And the one I've axiomatized as a warn-up here is the notion of opotopic type associated to the identity monad on types. But you could associate. There is a notion of opotopic type which incorporates symmetries, which essentially is the opotopic types associated to the E infinity monad.
Oh, I see. So I would go back and actually change the type theory.
Yeah. So I would generalize. So in fact, there's a universal choice because and maybe this is something I wanted to say also. There's a universal choice, which is that actually it can go even further than that. The E infinity monad is just one way to describe it type theoretically is it's the universe of finite sets together with sigma of finite sets. That is a description of the E infinity monad from a type theoretic point of view. But there's no reason to restrict to it being finite. In fact, the universe of types together with sigma is just the terminal infinity Cartesian polynomial infinity monad. It's just it's the biggest one, and so that gives you a canonical definition of opotopic type, which is opotopic type for that monad, not for the identity monad, which is somehow like the smallest or initial one, but for the terminal one. And so those opotopic types would cover all higher structures whose arities are allowed to be arbitrary types. And so there you can see the E infinity monad as a sort of sub-object of that monad consisting of the finite types. But that's the really general one. And something really nice happens with respect to that, which is that I sort of argued that I thought opotopic types are somehow the like natural extension of the way people think of ordinary inductive types to higher dimensions. And this opotopic type over the terminal monad makes this very precise because the way people think of the data of an ordinary inductive type definition is what's sometimes called an indexed container or a polynomial. It's just a collection of type families of a certain form. And if you take the definition of opotopic type over the terminal monad and unfold it once, it is exactly the definition of indexed container. So in other words, the continuing opotopic type over the terminal monad is somehow, for me, like the canonical continuation of what you should mean by higher inductive type, because it generalizes the classically accepted definition of what is an inductive type. Anyway, but that's just to say that but by passing to these slightly more exotic opotopic types, you drastically increase the number of structures that you can describe in terms of them. Does that answer the question?
Yes, and do you claim that all of this you know how to handle, or would that
that I know how to handle it.
Like I understand you somehow implemented this open monad, which lists the identity one. Can you do you know what to do for the terminal one, or is
I've been hacking so much on Agda trying to get the identity one work that I haven't gotten to that step yet.
But you think it's straightforward?
Basically, I think it's straightforward. Essentially, what you need to do is take the things that I said, these laws, and you'll need to render them associative. And what that amounts to is rendering sigma of types definitionally associative, because that is the monad law on the universe. I don't see any particular reason why that should be problematic. Now, people don't do that in type theory as it is right now, but I don't see any reason that should be particularly problematic. Because, for example, people render pi definitionally associative, but not sigma. So anyway, so it's sort of in terms of an equational theory that you would have to write down and understand the computational aspects of. I don't think it's particularly problematic. I think it just needs. I think it needs someone to sit down and do it and work out the normal forms and make sure it's still terminating and this kind of thing, and implement it. As I say, but implementing it from scratch is a very large project, and that's why what I've been doing to this point is trying to modify an existing proof assistant, and that has some limitations on it to what you can do. Yeah.
All right, thanks, John.
Okay, any other questions? David?
Sorry, two little questions. Well, one is little. You said that pi is treated as just mentally associative. In what sense is that true?
Beta reduction sort of computes definitionally. It's so you don't have the possibility with the constructor of pi to have it be sort of definitionally associative, but at least the term constructor computes definitionally, right? I mean, I'm just saying that like composition of functions is somehow is definitionally associative.
Okay.
Right? I mean, what's that?
Yeah, I don't see how that comes. I don't see how that comes directly from the. I mean, the type is not definitionally.
It's true. It's true. In fact, I'm not even sure it would completely make sense for the type itself, but whereas it does for sigma. So I agree with you. The analogy is not completely perfect.
In the way that function composition is definitionally associated because it's based on substitution, we could make sigma definitionally associative by, I don't know, removing all the parentheses in our pairs. So that
exactly. So the type checker would always sort of reduce pairs by associating them always to the right systematically.
Yeah.
I mean, as an equational, so I'm not sure what this would do to the type theory. Also, I should say this may not be the only way to implement the kind of thing I'm talking about, but imagining a type theory where that's the case is not so hard. I mean, I computationally speaking, I don't think that's a particularly difficult problem somehow.
Well, it would also be just great for quality of life, like, you know.
Maybe so. I mean, sort of. I guess the kind of theme that I'm sort of developing here is right. There's this large space of definitional inequalities that we can put on our type theory, and you know, we're trying to make it work to describe the structures we want, and it looks like so far we haven't added enough in order to describe the structures we want. And that's why, for me, going beyond what we currently have is not particularly problematic. We're experimenting and trying to find something which axiomatizes the structures we want. So, and again, you know, and I don't think there's a sort of like, I guess my analogy with pi is to make the analogy like this, right? Like it doesn't, you know, even if types are all homotopy types, it doesn't kill the homotopy theoretic information to have functions compose associativity, like definitionally associative. That's not a problem. And neither do I think that, you know, having the system systematically associate pairs to the right, both in the type and the term, I don't think this will destroy any homotopy theoretic information because there's essentially none there. So that's why I think developing a system which had that property is not particularly problematic. Anyway, yeah.
Thanks. And so right, my second question is, do you think that this approach could? What if I like a different kind of familial monad, right? What if I really am a simplicial person and I think simplicially and I can't learn?
Yeah. So then in that case, I think, yeah. So I think something sort of analogous probably works, but I don't know exactly what it is. So. So for example, right here, yeah, so we're looking at the page right here. One of the cool things and one of the things I like about opitopes is like the things that I end up strictifying are things that sort of make sense to strictify, or at least to me, from a sort of functional programming or type theoretic sort of point of view, right? So I have these monads, and these monads, the things that I'm strictifying are the operators which make the forms of higher dimensional definitions well defined. It makes sense to me that those would be sort of strict. But there's something that I don't do, which is there's the category of opitopes, and this category has a bunch of face maps and so on inside of it, and those will have a bunch of equations. Those faces will have a bunch of equations, but I don't strictify directly those equations, right? Instead, I strictify this algebraic structure, which sort of gives rise in a once removed fashion to that kind of structure itself. But if I wanted to do simplices or cubes, I'm not sure what I would replace that with. It seems like I just have to strictify the face relation somehow. And maybe that works. Maybe that's totally fine. I don't 100% know, but I'm saying it's not immediately of the same form somehow. You end up having to strictify something slightly different. And I don't know what the analog would be for these sort of monadic operators. But it's totally plausible that this idea of building an internal type theory of presentations would work for any shape you want, with a little bit of like sort of engineering and thinking about what equations you needed. I think that's totally plausible. Yeah.
Thank you.
Great. I see no more questions.
Oh,
Okay,
yeah,
let's thank Eric again.
Oh, sorry.
Yeah, Adrian, go ahead.
Yeah, sorry. Yeah, so I have two questions. So from what I understand, you've built this machine where you can plug in some monad, and then you get a different flavor of open-topic type theory. So I was wondering if there's some monad which you can plug into your machine, which will output something which makes it easy to axiommatize some sort of infinity categorical version of virtual double categories.
Okay, so yeah, so the machine which so currently the machine I've built picks that monad. It picks the identity monad. There should in principle be a machine which does what you say, but yes, but I haven't built that yet. What I'm saying,
Okay.
what I'm saying is that theoretically exists, but I've built the one which starts with a fixed monad to begin with. I don't think there's one that's going to spit out double categories directly from open-topic types as I've defined them here, even if I were to go to a more general monad. But what does happen is that once you generalize a little bit to one of the more general things I've talked about, so like Urs was saying, the E infinity monad, so these would be monads whose arities are finite sets, or the terminal monad whose arities are arbitrary types. Then it turns out that the notion of monad itself, the notion of Cartesian polynomial monad itself, is a particular kind of open-topic type. So it can be defined as, in other words, this is crazy sort of thing where, symmetric operads are algebras for a symmetric operad. It's essentially the same sort of thing, right? So open-topic types have this property that that you can use them to define what you mean by Cartesian polynomial monad, which is really sort of kind of crazy. So I think that if you needed to do something more general, if you wanted to talk about other monads and their algebras, the way I would do it is I would first use the sort of universal open-topic types to define what I mean by polynomial monad.
I see.
Define the one for virtual double categories, and then define them as algebras over that monad. So the sort of goal here is to sort of bootstrap that ability to talk about more complicated algebraic objects by giving us presentations which are general enough to talk about arbitrary algebraic objects. Does that answer the question?
Yeah, absolutely. Cool. So and then I just wanted to ask, can I read about this anywhere at the moment?
So I mean, the most recent incarnation, this kind of stuff I've talked about today, is not yet written up. I apologize for that. I'll send the slides to Urs. He can put them online. I was hoping to submit a paper on that this winter, but it turns out I'll be moving, so I'm going to be a little bit occupied. So it's in the works, and I hope this will be out soon, so you can check it out.
Okay, great. I look forward to it.
Yep.
Excellent. Any other questions? Okay, great. Let's thank Eric again for the very nice talk.